Hello, good evening. I hope I'm audible to you. So we will start our session regarding the doubt clarification and the problem practice session today. So this is we are into week 4 in the course of wastewater treatment and recycling, and I'm Akash Saha. I am one of the teaching assistant for this course. I'm a PMRS scholar currently pursuing my PhD in environmental engineering in the Hello. Parth, Parth, please mute. Saket, is the volume low, or please increase your microphone volume? I think it will be
Sir,
better.
please increase volume.
Yeah. Have you increased your volume in the system? Uh, I think this is the maximum I can go. I hope it's audible right now. It is okay. So if we see the overview of week 4, we have learned about the fate and transport of the contaminant discharge in the river. So we saw the natural purification system, different types of physical, chemical, and biological purification processes, and also the Streeter-Fels equation. And then we moved on to the calculation regarding various BOD received in the stream, COD and BOD calculations. And then we moved on to the concept of mass balance, where we have done mass balance applications also for specific reactors like CSTR, PFR, etc. So this was the whole overview of this week 4. So do you want me to solve numericals at first, or should I start with some theory MCQ type questions? Or we can directly go into the numericals. I have shared some numericals yesterday with some of you. So can I know, should I start with the numericals? Hello, am I audible? Please write in the chat box. Then we can directly go into the numericals. Okay, so I hope you have your pen and paper ready with you. Okay, so this is the first question, which says a plug flow reactor will treat completely biodegradable wastewater of BOD 350 milligram per liter to discharge standard of 20 milligram per liter. Okay, so the flow rate is 1 mld. You have to calculate the volume of the reactor if the rate constant is zero point 0.4 per hour. So this is the first question. It's a PFR reactor. The influent and the effluent BOD is given, and the flow rate is 1 mld. So if you want, we can work out the problem together. Is anybody trying, or I should do the working out?
Sir, I'm trying.
Okay. Aditya, what about you? Okay. Okay, so here I will also try to solve this question because I don't have the ready-made solution for this. So we can work it out. So the A part, it says that we have a PFR reactor. Okay. So we know the general equation of any mass balance equation. So it will be V dC by dt equal to Q influent into concentration of influent minus discharge of the outflow into the concentration in the outflow. Okay. minus because it's a non-conservative type of pollutant, so it will decay. So it will be V dc dt of the reaction. Fine. And here we know it's a first order decay. We have been given the decay constant as zero point 0.4 per hour. So we know it's a first order reaction. So my dc by dt of the reaction will become as, what will be my dc by dt of the reaction? Can someone tell? Anyone?
Sorry, sir.
What will be my dc by dt of reaction in this equation?
Minus
My
V
my
K
v
C by
by
V.
y
Minus V K C.
minus kc, right? It will be minus kc. Okay. And for steady state, my dc by dt of the whole reactor will be equal to 0 because it is a steady state. So this will become 0. This will be equal to minus kc. Okay, fine. Or you can write kc because I have already included the minus sign before. So how will my equation will change? It will become q in into c in minus q out into c out minus VKC. So if we solve this equation, we'll be getting as C out equal to Cn into e to the power minus kV by Q. So this is the equation that we got. So my volume V will be equal to minus Q by K ln of C out by C in. Is it clear? I hope it is clear for you. So if we substitute the formula, we know that it is 1 mld. So we can write it as 1000 meter cube. Okay. And it is per 24 hours. And my K value will be zero point 0.4. That is also in per hour into ln of C out is my 20 and C in is 350. So if we solve it, what is the answer that we are getting? I've solved it fully. Just tell me the answer. What is the volume that we are getting? Now, if people even trying this question, just calculate and let me know what is the volume.
298.
Yes, so it will be around 298.146 meter cube. So this is the volume of the PFR reactor, which will degrade from 350 milligram per liter to 20 milligram per liter. Now in the same question, so now in the same question, if we want to do like what will be my volume of a CSTR? Okay, so we have the same question, same conditions, everything will be same, but instead of PFR, we are taking it as a CSTR. So what changes will you think in the equation will happen? So we have the same equation. I will write the equation again. V dc by dt is equal to q in c in minus q out c out minus vkc. I am writing it directly. Vkc. Okay. So here, what change will happen in the case of a CSTR? What assumptions do we have for a CSTR? So in the case of CSTR, my C out will be equal to the concentration in the system, because whatever the concentration will be in the reactor, the same concentration will be my outflow concentration. And also, again, it's a steady state reaction, so this will become zero. So it will simply become as Q in, C in, and my Q out and C out are same. So no need, we can write QC in will be equal to Q plus KV into C, right? So my C will be equal to C in into Q by Q plus KV. So from here we can find the volume again, right? So what will be my volume in this case? In case of the CSTR, just substitute the values and tell me. We have to find the V, volume. So other parameters we know. So what will be my volume? This is the B part of the question, same question. Prashant, I hope you are understanding the problem.
In middle I joined, sir. That's why it's still
Yeah,
confusing
yeah.
here.
So here we are talking about a CSTR reactor, okay, in which the input concentration is 350, okay, and the output, that the C out concentration is 20 degree, and we have the rate constant as zero point 0.4 per hour, and the Q is given as 1 mld. Okay, so we have to find the volume of the reactor. So this is the question. So we have the basic equation of mass balance equation, and according to the CSTR condition, we have changed the equation, and we found like what will be my equation for the CSTR. So in this equation, if we input all the
Okay.
values, we will get the volume of the CSTR reactor. Saket, did you get the volume of the CSTR reactor?
Yes, sir.
Tell me.
5,000.
5,000. How 5,000 it's coming? Did you divide by 24 your MLD?
Yes, sir.
Please recheck. It will be around 1718.25. Okay. Please recheck your calculations once more. It will be 1718. Okay. So this is the volume of my CSTR reactor. So this is my V CSTR, and my VPFR was around 298. Okay. So you can see that from changing one type of reactor to another type of reactor, how much volume difference is coming. So if we see the ratio of the CSTR by PFR, 298.14, it will be around 5.76. So my CSTR reactor will be 5 times of my PFR reactor. So this is the takeaway we can take. Like for similar conditions, my CSTR reactor will be 5 times of my PFR reactor. Okay. So some things which we have to take care while designing any wastewater systems. Okay. So these were the answers. So we will move on to the next question. Okay. So the next question says that we have 3 CSTR in series, with the second reactor being twice the size of the first and the third reactor. We have 3 reactors here. So the second reactor is twice of the first and the third reactor. The pollutant concentration which is coming is 150 milligram per liter, and the flow rate is around 400 liters per minute. And the rate constant is 0.007 per hour. And so we have to calculate the removal efficiency of each of the reactor if the overall removal efficiency is 80%. Okay, so we have 3 reactors here in series, 3 CSTR reactors, where the second reactor is twice the size of the first and the third reactor. So my first and the third reactor are identical, and second reactor is 2 times of them. and we have all the concentrations and rate constants given and the flow rate. So we have to find the individual efficiency and also the corresponding HRT. What will be my corresponding HRT? That also we can find out. But let's focus on only the removal efficiency first, because again then the HRT will be the simple formula. Shall we see how to solve this problem? I will work it out with you. Do you have any question regarding the problem? Any query that you are not able to understand?
No, sir. Okay, okay.
Okay. I hope these questions will be helpful to you. So this is the 17th problem that we are doing. So here the influent concentration C naught is 150 and effluent concentration we are saying we need 80% removal efficiency. Okay, so 80% removal efficiency means 20% will still be there. So zero point 0.2 into 150. So it will be equal to 30 milligram per liter. Okay, and my Q is 400 liters per minute. So if I change it to into hours, so it will be 1 minute. Okay, so huh, I hope I am audible. So if I change into liters per hour, it will be 24.
How, sir, how to get concentration efficiency?
Sorry, I didn't get you. The effluent concentration, CE, you are asking. Saket, are you asking about CE?
Yes, sir.
Ha. So in the question, it was given that the overall efficiency was 80%, right? So at the end of the three CSTRs that we have, it should give an 80% efficiency. So my influent concentration was 150. Okay. So my at after 80% of degradation, 20% will still be there, right? So I have multiplied zero point 0.2 into 150. Did you get it?
Okay, sir.
Huh. Okay. So my Q value is this, and we know that my volume 1 will be equal to volume 3, let it be V, and my volume 2 is equal to 2 times of V. Okay. So we have just seen the CSTR reaction. So in terms of like, so let this be my reactor. So here this is C naught is coming, and from here CE will come. Okay, so inside this reactor will be C1, outside will be also C1. Here will be C2, outside also C2. Here it will be CE and it will come out as CE. Okay, these are the, and volume of first reactor is V, second reactor is 2V, third reactor is again V. So this is the basic schematic of this. So influent 150 is coming in and effluent it is 30 milligram per liter. So we have to find the efficiency of each the reactors. So that means we have to find C1 and C2. So we have to form equations with the help of these concentrations. So we have just now seen the equation of a CSTR. So in terms of so for the first reactor we will make the equation. So my equation will be C1 by C naught will be equal to 1 by 1 plus kV by Q. I hope you know how this equation comes. This is the same equation that we derived in the previous uh, problem. So similarly, This is the equation for the first reaction. So we got one equation in terms of C1 and C0. Second equation, again we will write C2 divided by C1 will be equal to 1 by 1 plus kV. So instead of kV we will take 2V because the volume is twice in the second reactor. So this will be my second equation. Okay, and my third equation will be having Ce by C2, which will be equal to 1 plus 1 by 1 plus Kv by Q. So this will be my third equation. So here we have three equations and we have three unknowns. So if we solve this, we will get the answer for C1, C2, and V also we don't know. So we will get all these values. Are you able to understand?
Yes, sir.
Okay.
Yeah.
Huh. So okay, we will move on to the solution. I will solve this and I will tell you. I hope you are noting down because I'll be erasing all the things after I have done writing them. So if we multiply all the equations, okay. So if you multiply all the equation, C1 by C naught into C2 by C1 into what? It will be Ce by C2. If you multiply all the equations, we will get 1 by 1 plus Kv by Q whole square into 1 plus K into 2V by Q. So these are the equations. This is so here C1 will cancel, C2 by C2 will cancel. So it will be ultimately Ce by C naught. So we know Ce, we know C naught, we know K, we know Q. So the only remaining thing in this equation will be volume. So we will directly get the volume from this equation. If we substitute all the values, we will get the volume as 1871.96 meter cube. Okay. If we solve it by calculator, we will get the volume as 1817.96 meter cube. So now to find the individual efficiency of each reactor, we will put that V value in the each of the individual equation. So first equation was my C1 by C naught, that is 150 will be equal to 1 plus 1 by 1 plus K, that is 0.007 into my reactor volume 0.96 into 1000 if I writing it in liters divided by 24,000. So if I solve this, I will get my C1 value. So my C1 value will come around 97 milligram per liter. So if you know my C1 value, so the efficiency for the first reactor will be 1 minus 97 by the influent, that is 150. So I will get around 35.33 percentage. So my efficiency of my first reactor mu1 will be equal to 35.33 percentage. Is it clear?
Yes, sir.
Okay.
I So can you solve and tell me the efficiency of the second reactor? Just substitute the values for the second reactor and tell me what will be my efficiency. So second reactor, again we will write C2 by C1. C1 was 97, 1 by 1 plus K, or we can write 0.00 what 007 into 2 into the volume divided by 1871.96 into 1000. I am changing into liter divided by Q, that is 24,000. So tell me what is C2. Solve and tell me what is C2. C2 and the efficiency 2. Tell me what is C2. I solved it fully. Just tell me the value.
48.
Okay, yeah, 40 it is coming for my, I got it at 46 milligram per liter. Okay, it might be little bit here and there because of some decimals. So it is 46. So what will be my efficiency? How much efficiency? You tell me as per 48. Tell me.
by 97.
97. Oh, you are telling, uh, what are you telling? The percentage or, okay, it will be 97. Yes, it will be 97. So how much are we getting? Tell me how it is simple. 52.577%. Okay, so the efficiency for the second reactor will be 52.577%. So similarly, we can solve it for the third reactor. Again, we will put the values in the equation and we will get this next reactor. Okay, so we will move on to the next question. So these are the efficiencies 35, 52, and 35 again. We'll get the same efficiency for the last one. Okay, so this is another question. The organic composition of wastewater, which is estimated as glucose of 100 milligram per liter, is reduced in a CSTR to 10 milligram per liter. And assuming that the degradation producing no net biomass growth and an oxygen content of 2 milligram per liter has to be maintained in the reactor. And the incoming wastewater has negligible oxygen content. So how much oxygen has to be supplied in the reactor for a first order reaction of 0.4 per day and the flow rate is 2 ml. So again, it's a simple question, like we have to go from the basics. It's a CSTR. So some wastewater is put into the CSTR. Okay. And in that, it has to be reduced from 100 to 10 milligram per liter, that wastewater BOD. And we have to now see in terms of oxygen because we have to calculate the amount of oxygen that has to be supplied in the reactor. And it is saying that 2 milligram per liter of oxygen has to be maintained in the reactor. Okay. And the wastewater flow is around 2 ml. So we will see how to solve this problem. I hope you understood the problem, right? Any problem with understanding the question?
सर क्वेश्चन एक बार फिर से बता दीजिए.
Okay. See, there is one, I will tell you. There is a CSTR reactor. In this, 100 milligram per liter of wastewater is coming in. And from this, 10 milligram of wastewater should come out. Like in terms of BOD, I am saying. So our first criteria is from 100 to 10. Okay. And for running the CSTR, we have to provide aeration, we have to provide oxygen to the bacteria. So now we are talking in terms of oxygen, like how much oxygen has to be supplied in the system so that my BOD get reduced from 100 to 10. So we have to see this question in terms of oxygen demand. In all other questions, we will see in terms of the contaminant, in terms of BOD or in terms of concentration of the pollutant, everything. But now we have to see in terms of oxygen. So we will change our equations in terms of oxygen. We will apply the same mass balance concept here, and we will find out how much oxygen has to be supplied in the reactor so that my COD or BOD get reduced from 100 to 10. And also it is saying that in the CSTR we have to maintain an oxygen of 2 milligram per liter. So now is it clear for you?
Okay, sir.
Okay, so we'll see how to solve this problem. So it is saying that my pollutant is glucose. So we know it is C6H12O6. And if you write the formula, it will be 6O2, it will give 6CO2 plus 6H2O. Okay, so this is my degradation. So if you see the molecular weight of glucose, it will be around 180. And if you see the molecular weight of oxygen, 6 oxygen, it will be around 192. So it means that for 180 gram of glucose, we need 192 gram of O2, or we can say for 1 gram of glucose we will need 192 divided by 180, which will be equal to 1.07 gram of O2. So we can say 1.07 gram of O2 is required per gram of my glucose. Okay, so till now is it clear? Please write it along with me so that the concept will be clear for you. So per gram of glucose we need 1.07 gram of oxygen. So this is the first part. Okay, so now let's see the next part. I will just remove this part. So now the total COD will be consumed, but total oxygen that is required to degrade from 100 to 10. So it will be equal to my total COD consumption will be around 1.07 into 100 minus 10, because influent is 100, effluent is 10. So it will be 1.07 into 100 minus 10. It will be 96.3 milligram per liter. So this much COD has to be removed in the system with the help of oxygen. Means in terms of oxygen, this much oxygen is required. And also there is a need to maintain, we have to maintain plus 2 milligram per liter in the reactor. This is in the reactor. Okay, so now we will make the mass balance. Okay, so if we make the mass balance, we know V dc by dt will be equal to Q into C. Now here C I am taking in terms of oxygen. So it will be C oxy that is coming. So C oxy in plus how much oxygen is supplied. This we have to find out. How much oxygen we have to supply. Minus how much oxygen is consumed. Okay. Minus Q C oxy that is coming out. So this will be my mass balance equation. So first we will see how much oxygen is coming in, how much oxygen is supplied, how much oxygen is consumed, and how much oxygen is going on. So in terms of everything, I have written the mass balance equation. So when our system will be in steady state, this will be equal to 0. Okay, and also with the wastewater, there is no oxygen is coming. So my C oxy in will also become 0. because with the wastewater there is no oxygen coming in. So it is 0. Now oxygen supplied, this we have to calculate. Okay. And can someone tell me what is the oxygen consumed? We have just find out. So what is the oxygen consumed here? Can someone tell me? Are you get understanding the problem? Is there any difficulty? Please let me know. Hello, anybody there?
सर एक बार शुरू से एक्सप्लेन कर दीजिए फिर से.
Okay, शुरू से. Fine. See, this is my CSTR reactor. Okay, in this 100 milligram per liter of BOD in the wastewater it is coming. Fine. And after my CSTR reactor, only 10 milligram per liter of BOD is remaining. So from 100, it is changing into 10. Okay, this is the BOD, the strength of the wastewater. Now in CSTR, we are providing oxygen because how the microbes will work. Without oxygen, they cannot work, right? So we have to provide oxygen. So in this question, they are asking like how much oxygen is required to be given in the system so that my BOD change from 100 to 10. Is it fine?
Okay, sir.
Okay, so this is the overall question. So now I told you that I hope you understood per gram, like 1.07 gram of oxygen is required per gram of glucose. This was clear, right?
Okay.
This was clear. So per gram of glucose. Now in this equation, if we want to see what is my COD consumption, how much COD, how much BOD has to be consumed, like how much oxygen will be consumed. We know it for sure. That is from 100 to 10. So 100 minus 10 is the total oxygen that will be consumed into 1.07. So it will be equal to 96.3 milligram per liter. So this is my total COD consumption. Okay, so now if you see the mass balance equation, it will be V dC by dt first Q into C in. Okay, so how much oxygen is coming in? Oxygen that is coming in. But we know that no oxygen is coming in with the wastewater, it is 0. Plus oxygen that is supplied. This we have to find out. Minus oxygen that is consumed minus Q C oxy out. I hope now it makes sense, Saket.
Yes, sir.
Ha. So at steady state, this will also will become 0. Now the total oxygen that is consumed. Okay. So the total oxygen consumed, this part we will calculate. So the total oxygen consumed will be equal to the volume of the reactor into the COD consumption. This is milligram per liter into, if we multiply it with some volume parameter, it will give my total total oxygen consumed. Fine. So now we have to find the volume. What will be my volume? So again, finding volume is very easy. We know it's a CSTR reactor, so we can directly put in the formula for a completely mixed CSTR reactor. We know Ce by C naught is equal to 1 by 1 plus kV by Q. Okay, so here my C is 10, C naught is 100, equal to 1 plus 1 by 1 plus zero point 0.4 into V divided by how much? It is 2 mld, so 2 into 10 to the power 6. 2 mld, so it is 2 into 10 to the power 6. So from here we can find the volume of the reactor. So my volume of the reactor will be 45,000 meter cube. Okay, so I told you, so how much volume oxygen will be consumed? So oxygen consumed will be equal to 45,000, okay, meter cube per day into 96.3 milligram per liter, or we can write gram per meter cube. So ultimately it will come as 4333.5 kg per day. So this much amount of oxygen will be consumed. Is it clear? Is it fine?
Yes, sir.
Ah, okay. So now again we have to calculate a few more parameters. We will do that. Just wait a minute. Okay, so in the equation we know V dc by dt, this will be equal to 0. So it will be 0 equal to Q in C in was also 0. So equal to 0 plus oxygen that is supplied, fine, and also minus oxygen that is consumed, that we have just found out 4333.5 kg per day, minus Q out into C oxy out. So we have to now calculate this C oxy out. If we know this, then we will calculate the oxygen supplied. So what will be my Q out into C oxy out? So it will be 2 into 10 to the power 6, okay, liters per day. This is my Q into, we know, we have told that we have to maintain 2 milligram of liter in the reactor, oxygen. In the question it was given. So it will be 2 milligram per liter. Okay, and if we change milligram to kg, it will be minus 6 kg per milligram. So directly substituting, we will get 4 kg per day. So my Q out into C oxy out will be 4 kg per day. We will substitute the value here. So if we substitute the value here, we will get oxygen supplied will be equal to, this all will go here. So 4333.5 plus 4 equal to 4337.5 kg per day. So this much amount of oxygen has to be supplied in a CSTR reactor to degrade my wastewater strength from 100 to 10, and also maintain 2 milligram per liter of oxygen in the system. Is it clear? You will have this video uploaded in YouTube, so you can go back and listen from the start. If you have missed any part, you will be able to understand, I think. It's a big problem, but it's an interesting one. Shall I go to the next question?
Okay.
Okay. Okay, so it's a very simple problem. Please try to finish it off fast. because we have already spent around 1 hour in the numericals. So a 24 meter cube reactor operating in plug flow mode reduces the BOD from 250 milligram per liter to 10 milligram per liter in 10 hours of detention time. So if the rate constant is 0.23 per day, what is the order of the reaction? So you have been given every parameter, but here you have to find out what is the order of the reaction. So it's basically a trial and error method kind of question. So we have learned about three types of reactions. One is the zeroth order reaction, first order reaction, second order reaction. We know the equations for everything. We have to just substitute the values and see whether we are getting the same values in the question. We will see this problem. So shall we start? Can someone tell me for a PFR reactor, if my rate of, if my order of reaction is 0, so what is the formula? What will be my CE? Can someone tell me the formula? It will be C is equal to C naught K into time. This is for zeroth order reaction. For n equal to 1, my C will equal to C naught e to the power minus kt. This is for my first order reaction. For n equal to 2, it will be Ce, or rather we can write it as 1 by Ce by 1 by C naught plus k into t. So this is my first reaction, second reaction, third reaction. So what you can do, we know that uh, that in our system my C naught is equal to 250, my K is equal to 0.23 per day, my T is equal to 10 hours. Okay, so these are the information we know, and we also know my CE value, that is 10 milligram per liter. So now for this time we will forget about the value of CE. We will put these value in the equations and try to find out the CE for each of the reactions, for each of the order, for zeroth order, for first order and second order. We will see, we will put these values and find out the CE value. C. So if my CE value is matching with 10 milligram per liter, that means that is my order of the reaction. So can someone please tell me what is the CE for zeroth order reaction? Just substitute the value and tell me what is the CE for zeroth order reaction. Everything is there written here. Just tell me what is the. Hello, is anyone trying? It's a simple problem. Tell me. Hello, anyone is there? 9.2 into 10 to the power minus 3. Uh, I think you have not changed the units because time is in hours and k is given in days. So you have to be careful.
Sir, 249.904.
Yeah, zero point 0.9. Yes, 249.9. So this is not equal to 10 milligram per liter. So we know that zeroth order reaction is not the correct answer. Now try for first order reaction. See what is the C in the first order reaction. Tell me fast how much. It's a simple calculation. What is C?
227.
Yes, 227. 227. Again, it is not matching. So now try with the for the third second order reaction. Just substitute. It's a simple one. 1 by C is equal to 1 by C naught. So tell me what is the C in this case. What is the C? So this is not the answer. This is also not the answer. Let's see what is the C in the case of second order reaction. Please tell me, Aditya Abdul. You can also try it. It's a straightforward question. I don't think that you people are sitting with the calculators. Maybe that's why you are taking so much of time.
10.016.
Yes, yes, it is 10, 10.016 or whatever it is 10. So here we see that we are getting the C same as what is given in the question. So that means this is my order of the reaction. So my order of the reaction is second order reaction. So this is how we can check what is the order of the reaction. Fine. So these are some of the numerical problems that I had. Okay. So we'll quickly discuss some theoretical problems and we will move on. Okay, because we have done enough numericals. Maybe if time permits, we will solve one more. Okay, so this is the first question. Identify the incorrect pairs among the following. So we have physicochemical process, oxidation reduction, biochemical process, sediment transport, physical process, filtration aeration, none of the above. So what is incorrect in these? Aditya or Abdul, can you answer? I hope you are listening to the questions. Please use the chat box because I am seeing only Saket responding. You people can also try. It's a pretty simple question.
Biochemical process and sediment transport.
Yes, it is true. But others also please try to answer these questions. It is very simple. So biochemical process. So sediment transport is not a biochemical process. It's a physical process. Other pairs are okay. Okay. A flowing river is an example of completely stirred tank reactor, continuous flow stirred tank reactor, plug flow reactor, batch reactor. So a river is a type of what reactor?
Plug flow reactor.
Plug flow reactor. Yes, Aditya is also saying it's a plug flow reactor. It is fine. Okay, so we will see the right answer is plug flow reactor, and because it's a long channel, so in that only radial dispersion or mixing happens. Longitudinally, we will take it as a CSTO. Now, arrange the following zones formed in the aquatic body receiving polluted water according to increasing dissolved oxygen content. We have to arrange in terms of increasing dissolved oxygen content. So we have clear water zone, decomposition zone, recovery zone, septic zone. So in terms of increasing dissolved oxygen. So which one of these will have the least dissolved oxygen? Can anyone tell me which one will have the least dissolved
Oh,
oxygen?
what option?
Option?
Option 4.
Option 4. So, okay, Aditya is saying it as B. Okay, Aditya, we have to see in terms of increasing dissolved oxygen. So first will be the least dissolved oxygen. So in septic zone, there is a possibility of the least dissolved oxygen because we will get the that minimum dissolved deficit point. So it will be the least dissolved oxygen, and then it will be decomposition zone where it will having more dissolved oxygen than the septic zone, but still less. And then we will have the recovery zone where it is recovering from the dissolved oxygen. We are getting more and more aeration and dissolved oxygen. And then at last it will be clear water zone. So option D is correct. Okay. Again, oxygen deficit D at any time in a polluted water body is computed as minimum DO, saturation DO plus actual DO at constant pressure, saturation DO minus actual DO at constant temperature, saturation DO minus actual DO at constant pressure. So oxygen deficit is defined as what?
Saturation DO. minus actual DO at constant temperature.
At constant temperature, yes. So we have to be careful. It is at constant temperature. So C is my correct answer. Okay. Identify the zone in water body which is least favorable for sustaining aquatic life.
Sir, is there any significance of pressure?
Signification of pressure, like, see, it is just for the calculation problem. See, with respect to pressure also, the DO will change. Okay, it can change. But here, for calculation purpose, we are saying that saturation DO minus actual DO at a constant temperature will be defined as my oxygen deficit. So, as per definition, we are going. If it were defined as at constant pressure, then it would be the same. Because with pressure, also the DO can change. So, identify the zone which is least favorable for sustaining aquatic life. So, among these options, what is least favorable? So, it is similar to our one of the previous questions. We have, if it is least favorable for aquatic life, that means it will have the least dissolved oxygen. Yes. So, it will be, Aditya says, it's decomposition zone. If septic zone would have been in the option, then the answer would be septic zone. But here septic zone is not there, so it would be decomposition. Okay. Physical processes for self purification of running stream are due to. So we have to identify which of the options have all the physical processes. So we are talking about physical processes. So which of the options have only the physical processes?
So option B.
Option B. Yes. Because others will have the coagulation. So it's the option B. Okay. The next question. Steady flow is no change in velocity with distance. Velocity changes with time. No change in flow rate with time in a stretch. Flow rate changes with time. So what do you mean by steady flow? When we are saying the flow is steady, what does that mean? Whether it changes with time or it changes with distance or there is no changes with distance or the flow rate changes with time, what is the option? Correct option.
Option B. Sorry,
Of
C.
C, okay. Yeah, it is talking about steady flow. So if it is steady, there will be no change. And it will be steady flow, so it is no change in flow rate with time. Okay. So it will be,
Sir,
huh.
sir, can you explain steady state?
See, steady state means suppose we are running a reactor, okay. In running a reactor, and we are providing some influent to the reactor, and we are uh, getting some effluent from the reactor. Okay. Suppose I am putting 100 milligram per liter of a contaminant and I am getting some outflow. Suppose 10 milligram or 20 milligram or whatever. So what steady state means is like irrespective of time, I will have uniform outflow or uniform uh, concentration, everything. So my concentration or my flow rate will not change with respect to time. So so even if I take the effluent at 1 o'clock or I take the effluent at next day 3 o'clock or whatever, if the system has achieved steady state, that means there is no change with respect to time. So it can be a steady state of flow. It can be a state. So in case of rivers, suppose a river is maintaining a flow rate of 5 meter cube per second. Okay, so steady state means throughout the time it will be 5 meter cube per second. It will not be at some point it will not be 6 meter cube or it will not be 4 meter cube. So with irrespective of my time, the flow rate or any characteristic that we are defining, be it concentration, anything, it will not change. It is with respect of time. Now, in the first question, in the first option, it is saying no change in velocity with respect to distance. So that is not flow rate. That is uniform or non-uniform. So distance means we are uh, considering two different points. Suppose at 1 kilometer or at 2 kilometer. It's a river. We are checking the flow rate at 2 points, point A and point B. So if it is constant in both the places, it will be a uniform flow. But for a steady flow to be happen, it should be same with respect to time. Is it clear?
Yes, sir.
Okay. Okay, so the next question is which of the following statements are true about plug flow reactors? Fluid is mixed in radial direction. There is negligible longitudinal mixing. Example is pipe flow or all of the above. So which of the following statement is true regarding a plug flow reactor?
All of the above.
All of the above. It's a pretty direct question. So it will be all of the above. Others, I hope it is clear. That's why I'm not maybe asking anything or responding. So please, if you have any doubt or any query, as Saket is also asking in between, you can also unmute and ask. Okay. So there is no problem in asking at any point of time. So it will be all of the above. Okay. When sewage enters the river, the rapid depletion of dissolved oxygen is due to. So we have put some sewage into the river. So we know there will be a decrease in the DO. So what is the reason? A. It is due to the change in temperature. B. Suspended particles. C. Respiratory activity of the aquatic plants. D. Microbial activity. So which of these options will result in a rapid depletion in the dissolved oxygen? Aditya is saying it as D. Yes, it is microbial activity. Okay, so due to the action of the microbes, because microbes need oxygen to decompose any organic matter. Okay, so they need oxygen for decomposing the all the suspended or the soluble organic matter present in the system. So D is the correct answer. Okay, so which of the following statement is correct? Conservative pollutants are stable and persistent in nature. Non-conservative pollutants are perceived as a bigger environmental threat. Inorganic pollutants are typically non-conservative in nature. So out of these three statements, which of the statement is correct? So you see the options, none of the statements, statement 1 and 2, only statement 1, all of the statements. So you have to tell me which of the statement is correct. So here we are talking about conservative and non-conservative pollutant. So if you may ask, non-conservative type of pollutant will not degrade with time. Okay, it will not decompose with time. Whereas a non-conservative pollutant will degrade with time due to several actions, physical, chemical, biochemical, or photochemical, anything, it will degrade.
Statement 1 and statement 2 are correct.
Statement 1 and statement 2 are correct. Okay. Why statement 3 is not correct? How will you change the statement 3 to make it correct? Here it is saying inorganic pollutants are typically non-conservative in nature. So to make this statement correct statement, what will you change? So we know that most of the inorganic pollutants are conservative in nature. So Okay,
Sir, why second is incorrect?
1 minute. Okay, yes. So second question, second statement is also incorrect. It is saying that non-conservative pollutants are perceived as a bigger environmental threat. Okay, so statement 2 is incorrect because see, non-conservative pollutants are able to degrade with time. So if any pollutant is able to degrade with time, then it will pose a lesser threat to the environment. Because suppose any organic pollutant you take it to consideration, you put it in river, so by the action of microbials it will be decomposed, so it is not a threat anymore. But if we have a conservative pollutant which will not degrade or will be not be acted upon with time, then it is a problem in the system. Are you able to get it? So I missed the second
Yes,
statement.
yes.
So non-conservative statements, non-conservative pollutants are not a bigger environmental threat. That's what it is saying. It is a threat, but as compared to the conservative pollutant, it is not a bigger environmental threat. It is in comparison. So until and unless it is getting decomposed, it is problem. But once it is getting decomposed, then it is not a problem for us. Okay, so it's a direct uh, question. We have to find the 5-day BOD at 30 degrees Celsius. So the ultimate BOD is given as 290 at 20 degrees Celsius. So ultimate BOD is given at 20 degrees Celsius. We have to find the BOD of 5-day at 30 degrees Celsius. And the rate constant is also given for 20 degree, that is 0.23. And the base is E. So tell me what will be my 5-day BOD. So first you have to do some temperature correction, and maybe then you can find out. Okay, so the correct option is D. We will see how it comes. So, so for K30, we have to find the 30-degree rate constant. So it will be K20 into 1.047 into T minus 20. That is 30 minus 20. So it will be 0.364. This is my K. So we know that BOD is equal to the ultimate BOD into 1 minus e to the power minus kT. So if we input all the values, we will get it as 243 milligram per liter. Okay. So I hope it is very easy and clear. Is there any problem with the solution?
No, sir.
Okay. Okay. Again, you have to find the ultimate BOD if the 5-day BOD is 223. So now the question has been reversed. We have to find the ultimate BOD if we have been given the 5-day BOD as 223. So the rate constant is as 0.26. So tell me what will be the answer. It's a very simple question. This is the answer. Are you able to get this answer? So for this question, there is no need to solve because my ultimate BOD will always be greater than my 5-day BOD. So we can directly take it as 306.5. Okay. So again, similar equation. So if we put all the values, you will get it as 5 WD, we know it is 223 is equal to U BOD into 1 minus e to the power minus 5 into 0.26. Okay. So again, it is asking about now the 3 WD. Again, we will put the same question. It's the same question, so I am not discussing it. Okay, so the next question, it is a important question. An industrial wastewater stream enters the stream having a BOD of 10 milligram per liter and flow rate of 20 meter cube per second. If the flow rate of wastewater is 1.5 meter cube per second and BOD concentration is 250 milligram per liter, what will be my BOD concentration at a point downstream after the point of confluence of the wastewater with the stream? So here they are saying that there is one wastewater stream, there is one normal river stream or anything. It is meeting at a, so one, for one the flow rate and concentration is given, for the other one also flow rate and concentration is given. Now after that it is coming out after the point of confluence. So what will be my BOD concentration after mixing? So tell me what will be the answer. Direct application, no need to memorize anything here. It's a conservation of mass, simple conservation of mass. So we know the BOD, let it be M1, BOD of wastewater 250 and flow rate Q1 as 1.5. Now the BOD of the stream M2 as 10 milligram per liter and flow rate is Q2 20 milligram 20 meter cube per second. So the BOD at the point of confluence will be M1 Q1 plus M2 Q2 divided by Q1 plus Q2. So it's a direct question. You will be getting the answer for this. Okay. So it will be 26.75 meter. Okay, so this is the last question that I have as a numerical. So this is the last numerical that I have. I think some people have joined just right now. So those who have joined late, let me tell you, I have discussed many numerical problems, like not even previous year problems, some of the major problems which I have sent you earlier as a practice questions yesterday. So I've already solved those questions and you will be able to get all the solutions in my YouTube channel. So just type in Akash Shah NPTEL and I will upload this solved lecture video and you will be able to access all the solutions of the problems. Okay. So till then you can solve this problem. So it is saying that a 400 meter cube CSTR receives the water from a single inlet at 40 meter cube per hour flow containing 20 milligram per liter of a pollutant. Let it be TPAH. So determine the steady state concentration. If it is degraded at first order kinetics, which is equal to K is equal to 0.23, it will be per hour, not hour, it will be 0.23 per hour. So it's a direct question of a CSTR. You have been given the Q value, the concentration value, inlet concentration value. So we have to find the steady state concentration. So by steady state concentration, we can say either it's an effluent concentration or the concentration inside the system. So here again the concept of steady states comes. So we will see the solution. So we know for any CSTR, the outflow concentration will be equal to the steady state concentration or the concentration inside. And for first order reaction kinetics, we have dc by dt equal to minus kc. Okay, so in the mass balance equation, if we input all these things, we will get q into cn minus qc minus vkc equal to 0. So we know q, we know every other parameter, so we can directly find the c value. So can someone tell me? Oh, I have already shown the absolute answer. So my C value will be equal to 6.06 milligram per liter. Do you want to solve another numerical related to disinfection I have sent yesterday? We still have some more time.
Sir, we need reactor type problems more.
Reactor type. What is like? What issue are you facing in these problems? Like, what is the current problem you are facing?
Sir,
You can tell me, that is not an issue. Like, is there any conceptual problem, or what kind of practice do you need? Because I have like solved every type, CSTR, PFR, first order reaction, second order reaction, everything we have covered.
sir, I want some practice for numericals.
Practice on numerals, you can take any previous year gate question paper, or previous year gate questions from any standard textbook. You can solve it directly.
Okay.
Okay, I have already sent you many of the problems, but if you want, you can directly take any gate or any standard books. Are you an environmental engineering student, MTech or BTech?
No,
Saket,
sir, I'm MSc Environmental Science.
MSc Environmental Science. So, which
Sir,
book do you read for wastewater? Do you have any standard book?
no, sir.
See, I would suggest you can try Metcalf and Eddy or PV and Rowe. Metcalf and Eddy or PV and Rowe, these are some of the textbooks, standard textbooks for wastewater engineering. If you see any of these books, you will get plenty amount of questions there. Okay, you go to your library and get these books. And
So
there is, sorry,
what is the name of book?
I will write in the chat box.
Yes, sir.
Metcalf and Eddy. So this is one of the standard book. You will get the e-copy also online. Okay, so Metcalf and Eddy you can play, or you can for PV and Row is a bit easy version, not much in detail, but for basics it is okay. So PV and Row is also another writer, so you can see this book. Any other doubt or concerns you have?
Sir, these are for wastewater treatment.
Wastewater, water, yeah, all the water treatment. I don't think explicitly PV and Row you will get, but Metcalf and Etty is dedicated to wastewater engineering. Okay,
Okay.
Kirti, do you have any queries? You have joined late, I have seen, because we have discussed many sample problems. If you have any queries regarding anything, you can ask me. You can unmute and speak.
Hi, sir.
Yes, yes, tell me.
Actually, I have missed the problems. No issue. I will go through the YouTube.
Okay, okay, no issues. So if you have
Thank you.
huh, any other conceptual, if you all three, if you have any conceptual problem regarding any of the reactors or any derivation, Streeter-Phelps equation is also a major thing in this. So I have a big problem related to Streeter-Phelps equation also. So if you people are interested, I can send you over mail. Okay, so Streeter-Phelps equation, there is a very big problem I have with me. So if you are interested in solving that problem also, we can discuss. I can
Yes,
send
sir.
it.
Yes, sir.
Okay, so I think I have this question right now. You try to wait. This is the question. Just take a screenshot of this question. I will give you some hints for today, how to solve this question. So just take a screenshot of this question right now and try to solve based on the hints that I am giving. Okay, then later we can discuss maybe in the next class or over mail. I will send you the solutions. That is not an issue. So it is saying that a municipal wastewater treatment discharges a secondary effluent in the surface stream. So we have a surface stream, and over it a municipal secondary effluent is being discharged. And it is saying that the worst conditions are during the summer month, and when the stream flow is low and the temperature is high. And they have made some measurements in lab scale. So it is found that the wastewater have a maximum flow of 15,000 meter cube per day, a BOD of 40 milligram per liter, and a dissolved oxygen concentration of 2 milligram per liter with a temperature of 25 degrees Celsius. So these are all the parameters of the wastewater. We have given the flow, the BOD, the dissolved oxygen, and the temperature. And also for the stream on which the wastewater is being like discharged. For that also we have the same parameters. We know the flow, it is 0.5 meter cube per second. The BOD is 3 milligram per liter. Dissolved oxygen concentration is 8 milligram per liter, and temperature is 22 degrees Celsius. So after complete mixing, the velocity is 0.2 meter per second, and the reaeration constant is zero point 0.4 per day. So we have to find the critical deficit. So we know that as per the Streeter-Phelps equation, there is a sag in the oxygen curve. So we have to find the critical deficit. So critical deficit means the point which have the lowest DO. So what is the difference from the saturation DO? So that deficit is known as the critical deficit. So we have to find the critical deficit and also the dissolved oxygen concentrations at 20, 75 and 100 kilometers. So I will just give you some basic hints on how to solve the problem, how to approach the problem. Okay. I hope you have noted down the problem. Otherwise, it will be very difficult. Okay. So we have for wastewater, I will write everything as W. So we have the QW, that is 15,000 meter cube per day. So you can change it as meter cube per second. Okay. I am not doing any calculation right now. I am just showing how to approach the problem. And we have the Q of the stream QS. So my Q mix will be QW plus QS. Okay. Now what will be my BOD mix? My BOD mix will be the BOD of wastewater into Q of wastewater plus BOD of stream plus Q of stream divided by Q mix. So from this I will get BOD mix. Similarly, once I get this BOD mix, this is the BOD, like the 5-day BOD. Okay, so we have to find the ultimate BOD. That ultimate BOD. So ultimate BOD will be, what will be my ultimate BOD? It will be my BOD mix 5 divided by 1 minus e to the power minus k2. So if you input all the parameters, you will get the ultimate BOD. So this is my ultimate BOD. Now again, we have to find the DO mix because the two again same DOW into QW plus DO stream into Q stream divided by Q mix. So we will get the DO mix. Similarly, again, we will find the temperature mix. We will apply the same equation and we will find the temperature. So we have the flow rate mix, the UBOD, DO mix, temperature. So we have everything ready to put into the equations. So these are all the basic input parameters that we get. Okay, so now the next part will be it is said that the conditions are critical during the summer and also the temperature mix we have got. So suppose we get the temperature mix as some x degree per Celsius. So now we have to find all the rate constants at x degree per Celsius because we know the rate constants are 20 degree per Celsius or 30 degree per Celsius, but we have to find for x degree per Celsius. So we will find the kx degree per Celsius and also the k aeration x degree per Celsius. Okay, so we know that K20 will be equal to 0.03. So from that we can find the Kx and also K reaeration 20 is equal to zero point 0.4 is given in the question. So with the help of these values we can find it will be 1.047 x minus 20. It will be Ka20 1.016 into x minus 20. Okay, so let this be K1 and let this be K2. Till this step, is it clear? Hello, are you with me?
Yes, sir.
Okay. So now we have to find that so at that x degree per Celsius, what is my deficit, DO deficit. So at saturation point, at what at 22 degree per Celsius, my desaturation will be 8.7. So my DO will be 8.7 minus whatever DO mix that we have got previously. So that will be my initial deficit. Okay, so in this way we will get. Now in the next question we have asked like what will be my critical deficit. So for critical deficit we know the formula. We know the formula. For first we will find the time of critical deficit. So Tc will be 1 minus K2 minus K1 into ln of K2 by K1 1 minus DO K2 minus K1 divided by K1 by my ultimate BOD that I got. So from this I will get my critical time at where I will get the deficit. So my critical deficit will be equal to K1 by K2 into my UBOD into e to the power minus K1 into Tc. So this will be my critical deficit. Is it clear? It's just first we have to find all the parameters because here we need to know what is K2, K1, D naught, UBOD, and all these rate constants at the particular temperature. So for that particular temperature, we have to find the mixed temperature Then only we will be able to find. So for all finding all these parameters, we have to do all the background study. And after that, we have to just input all the parameters. We will get the critical time first. And when we put the critical time in this equation, we will get the critical deficit. Is it fine? It looks a bigger problem, but once you start solving, it is a pretty simple thing. Okay. You try this problem out, and if possible, you can send me the solution through the mail, what you have got, and then I can share you the proper solution. Just show me that you have done something. Just don't ask for the solution like that. You follow these steps which I have told you. Try to solve whatever answer you are getting, you just send it to me. I will send you the proper solution, or we will discuss it in the next class. Okay. So that's all I had for today. If you have any queries, you can ask me, or you can mail me in my email ID. So the next session will be on 29th August, 7 to 9 p.m. So I will request everyone to please join by 7 p.m. Okay, because then we are losing time if you are joining late. So if you don't have any query, you can leave the session, or you can ask me if you have any queries. That's all from my side.
Thank you.
Okay. Kirti, Aditya, if you don't have any doubts, you can leave the session.
Okay, sir. Thank you.
Okay. Bye. Aditya, you have any queries?